Welcome back everyone to part 2 of our discussion on distribution plots. In part 2, we're going to code out the ideas we discussed in part 1. Let's head over to a Jupyter Notebook. Alright, here I am at a Jupyter Notebook. I've gone ahead and imported NumPy, Pandas, and Matplotlib.pyplot, and I've also imported Seaborn as SNS. So let's go ahead and read in our dataset we're going to be working with. We will go ahead and read in the same dataset as last time, which is just pd.read.csv, and inside the Seaborn folder, you should be able to find dm_office_sales.csv. So we take a look at the head of the data frame. We already know there's a division, level of education, training level, work experience, and then the salary and sales, and each row represents one employee. So let's go ahead and start looking at the distribution of some of these columns. To begin with, let's go ahead and check out the distribution of people's salaries. So one way to do that is with the most basic rug plot that we talked about. And to do that, it's just sns.rugplot. And as I mentioned before, typically you're going to provide your x and y variables, but in this case, a rug plot doesn't actually really have a meaningful y-axis. So in this case, we'll just say x is equal to the salary column, and data is equal to the data frame we just read in. And by running that, you should be able to see the salary produced. So here, what happened is we get a single tick for every single salary. And if these ticks are too small, you can always just edit the height. And this is done with the height arguments. And you can edit the height to be a percentage. So you can say, go ahead and take up 50% of the y-axis on the height. And again, notice that the y-axis values are changing, but they're not really meaningful here. All right. And sometimes people like to think of a rug plot as a one-dimensional scatter plot, because technically this is a scatter, but it's just happening along one dimension. So you're just having ticks there. And just like the other plots, if you ever want to edit something on the figure level, right before it you can say plt figure, and then we could edit, for instance, the fig size to maybe be, I don't know, like 5 by 8, and we could also edit the DPI if necessary to get more detail there. Okay, so clearly here we're editing the figure with plt.figure. So let's go ahead and move on to two separate plot types after a rug plot. Typically you're not going to be using just rug plot. So let's explore the dis plot and the hist plot. And I want to make a really important note here, is that in the latest version of Seaborn, as you begin to type DIS, you'll notice there's both DIS plot and DIST plot. DIST plot is deprecated, so you'll notice that we will be typing this plot without a T. So in the future, they will remove this plot. And instead, what they've done is they've made two functions. One is hist plot and the other is dis plot. Now I know this can get really confusing because they all sound extremely similar, but these are the two we're going to be using. Do not use, and I'm going to write it here, do not use DIST plot. This one will be deprecated in the future. And it should warn you about its upcoming deprecation if you're using the latest version of Seaborn. Okay, so let's begin with the distribution plot, which is sns.displot. So I'm going to say sns.displot. And let's go ahead and provide the data is equal to df. And since I'm providing the parameters, I don't need to order them in any particular way. And I'm going to go ahead and check out the distribution of the salary. So we run that, and you'll notice we get back the histogram. And so things I can edit about the histogram are things like the bin size or the number of bins. So I could say just have 10 bins only. And now we're just seeing the general trend. Or I could say give me 100 bins. So it's basically breaking up the x-axis into 100 even bins. And now we see we get maybe too much detail. But overall, it's up to you to edit the bin size. And this is probably the most common thing to edit for a histogram. Now you can also add in grids and styles for histogram. So sometimes with the default white background style, it's a little hard to match up the height of a histogram column with the y-axis. So if you want, you can always say above it, sns.set, and then decide on a style. And there's a couple of styles to choose from. One is dark grid, and you actually pass this in as a string. So the dark grid gives a darker background with a white grid. There is white grid, which gives a white background with a gray grid. And then there is the default white, which is just a plain white background, which is kind of what we saw. It also makes the actual histogram a little lighter. And then there's also dark, which gives a dark gray. And then there's also finally ticks, which essentially just makes ticks along the y-axis and x-axis. So again, that's SNS set style. And you should notice that once you set a style, for instance, if I set dark grid, run this, and even if I comment out dark grid, it has actually set the style for the rest of the notebook. So sns.setStyle is kind of a high-level command that will set the style for everything else in your notebook. If for some reason you want to reset this and don't like it and don't like any of the styles, you can always just come up here to kernel and say restart and run all with the set style commented out. So this will reset everything for you in case you want to go back to the default. So just keep that in mind, that's available to you. The other thing you should keep in mind is for things like editing color or line widths, etc., all of the arguments that we learned about in Matplotlib customization is actually available to you within the _plot call. So if I come and do Shift Enter here and expand on this, you'll notice that eventually beyond all of these, there's stuff like color, but there's also this keyword arguments. And this keyword arguments actually refers to the keyword arguments that are available for us inside of Matplotlib. So, for instance, I can say, go ahead and change the color to be red. And suddenly the colors are red. And I can also say, make the edge color something like blue. And then it's actually changing the edges here to be blue. And then just as before, I can also do things like set the line width equal to something that's a lot thicker, like let's say 4. And now we can see we're editing the line width there. And it can even take in line styles just as before. So like ls stood for line style, and I can make that a dashed line. Now, obviously, you would probably never actually have a histogram of a dashed line. That kind of makes no sense. But the important thing to note here is that many of the parameters that we are providing to Matplotlib are actually available within this plot or any Seaborn call. It's just important to note that it's not explicitly mentioned here, things like edge color or line width. In fact, if you scroll down here, you won't find them. It's because they're actually all here within the keyword arguments that link back to Matplotlib. Now, that doesn't mean that every single Matplotlib customization that we thought of or discuss is going to be available here. For instance, it doesn't really make sense to start editing things like the marker face because these aren't really markers. It's just a histogram. So keep that in mind. You should only be editing things that are relevant to the particular plot type. So this again was DIS plot. There's also hist plot. So let's go ahead and explore that one. They're very similar. And in fact, most of the time you're probably just going to use DIS plot, but there is sns.hist plot, which works really similarly. You pass in data is equal to df, and then say x is equal to, for instance, the salary column. You run that, and it creates the histogram. And if we take a look at what this plot by itself looks like, you'll notice that by default, they're essentially making the same thing. So it's kind of up to you if you want this plot or hist plot. This plot is a more generalized version of this histogram plot. So I recommend, and what we'll use throughout the course, is this plot call, which is just going to show us the distribution. Now what's nice about this plot call is if I wanted to, I could see the kernel density estimation plot on top of it by saying KDE is equal to true. And if you run that, it will show you this KDE. And what's also really interesting is you can not just see the histogram and the KDE, but if you really want, you can also say rug is equal to true. And here it will show you all three of them. It will show you the rug plot, the histogram, and the KDE. Whether or not it's particularly useful for you is kind of up to you. But again, the dis plot is kind of this higher level plot that shows all three options if you want. By default, it's just a histogram, but you can also put in the KDE and the rug plot. So let's talk about this KDE. Maybe in some situations we only want the KDE plot. How can we do that? Well, let me remove hist plot. We can say sns.KDE plot, and then same as before, we pass in the same data. So in this case, my data is df, and then my x is going to be equal to the salary column. Run that, and now I see just the KDE. And what I want to do to finish off this lecture is just build out the KDE plot, starting with a rug plot, then with a histogram, and then with the KDE. So let's just go ahead and create some example ages. So what I will do is say np.random.seed and set that to 42. And in the very same cell, I'm going to create some random ages. So we'll say np.random.rand int, And recall, rand_int takes in the lower limit, the upper limit, and then how many samples you want. So I'm going to say give me 200 samples of numbers or integers between 0 and 100. So I'm going to say these are just random ages that we sampled. So we run that, and if I take a look at sample ages, it's just this array of 200 ages starting at 51. And if you followed along with me with the same seed value as I did, 42, just an arbitrary value, you should have gotten 51 as well. Okay, so let's confirm this or change this into a Pandas data frame. I'm going to say sample ages is now equal to PD data frame. Pass in sample ages, and then say columns is equal to age. All right, so I now have this data frame, and it has the sample ages or age column. So now if I take a look at sample ages, I can see here it has this age column. So let's go ahead and start building this out. Well, what I could do is just do a rug plot of this to see how they're distributed. And we should expect a uniform distribution. More or less, you have the same probability for all ages. But because it's all random, there's going to be a little bit of randomness to this. So we'll say the data is sample ages and say x is equal to age. Run that. And so I can see I have a pretty uniform distribution. Looks like I'm missing some a little below 20 and a little above 60. So what I could do is say SNS distribution plot, DIS plot, same as before, pass in my sample ages, say x is equal to age, and let's actually now say rug is true. So I'm essentially building off of this original rug plot, but now I'm going to see the histogram on top of it. And if I want, I can keep editing the number of bins here to try to see more variation. So for instance, I could make this 30 bins, and now I see the variation. So now I see that drop in ages below 20 and that drop in ages above 60. And notice here you can see way less ticks on those particular bars, which is kind of interesting. Now the reason we are showing you can edit the number of bins is because there's actually an analogous argument in the KDE plot, which is editing your bandwidth for your actual kernels. So now that we understand this distribution of sample ages, the rug plot and the histogram, let's actually say KDE is equal to true here and see the KDE on top of this. So you notice what's interesting is that the KDE is immediately cut off below 0 and above 100 because there are no values there, which realistically is actually what we want. But in some situations, maybe you will have values below your actual limits. And in fact, if you say SNS dot KDE plot by itself and pass in sample ages of x is equal to ages, or age, excuse me, you do notice that by default, when you're plotting these Gaussian distributions right on top of each other, you will get some probability outside your existing range, as we discussed in the previous lecture. So if you do want to cut it off the way this plot is doing, what you can do is add a clip parameter. We can say clip from 0 to 100, and this will clip off the KDE. And essentially what we have here, we have this curved line, which is the same curved line shown here. Something to note here, though, is that the scale is kind of different because here, the scale has to be the count, versus here, the scale is the density. Essentially, what's the probability of picking someone exactly at 20? And it would be this probability right here. So that's what the density is really representing. It's the probability curve for picking someone at this particular age. And if you want, you can then start taking the area underneath it to get the probability of picking someone between, for instance, 20 and 40 years old. And then the last thing I want to show you here that I did mention is the fact that you can actually edit the bandwidth. You can adjust it. So you do this with bw_adjust. And if you make this a very small value, for example, 0.01, what's going to happen is with very narrow bandwidth, so very small values, you're having really skinny Gaussian distributions stacked on top of each of these rug points. So it's going to pick up a lot of the variance here. And so we can make this maybe a little larger. And now notice it's getting more jaggedy because we are picking up more and more of that actual variance. So it's essentially making those Gaussian distributions a little narrower. As you begin to make it wider, such as 0.5, you start to pick up less and less of the noise. You should be careful though, because if you make this too big, for example, if we make the bandwidth 2, then eventually you're picking up almost nothing of the signal, and more you're just going to get something that looks just like a big normal distribution, which may or may not be what you're actually going for. So let's go ahead and just make this huge. I don't even know if this will work, 20. And there you have it. So in reality, this is not what the data set distribution should look like. It should look like more even, more uniform here. And because we made our bandwidth so large, it's essentially starting to normalize to the overall Gaussians we keep adding up. So just keep that in mind. You want to adjust it so it's a reasonable choice. Maybe you want to show a little bit more of the behavior, so you want to manually adjust it here, or maybe you just want to keep the defaults. Okay, last thing I want to show you is another really common option is to shade this in. So if you say shade true, it will actually fill it in for you. So here, the parameters you may need to know for KDE plot is clip, bandwidth adjust, and shade is equal to true. Okay, so the main function call we're going to be using throughout the course is displot, because it's kind of the granddaddy of all these other plot calls. So it's the least specialized between hisplot and rugplot and KDE plot, which is why you can actually call rug and KDE within it. So again, for all these plot types, really displot is the main one we're going to be going for. Okay, that's it for distribution plots. I'll see you at the next lecture.